Now, electromagnetic waves are kind of a wormy little thing in terms of the discovery of science and physics here, which is that they're the only wave that doesn't travel requiring a medium. So every wave other than electromagnetic wave is a mechanical wave, meaning it requires a medium. So ocean waves travel through water. If there's no water, there's no wave. Sound waves travel, in this example, through air. If there's no air, you don't. But also sound waves can travel through water. Sound waves can travel through solid objects. Earthquake waves travel through the solid earth. So the idea is you can't have a disturbance in the medium, which is what a wave is, without there being a medium there to disturb. And so it was just widely known that electromagnetic waves must be traveling through some invisible medium called ether. This was widely known and got very popular in the 19th century. And then there was a very famous negative experiment, the Michelson-Morley experiment in 1887, that proved that there basically was no ether. And so this is why I bristle at people who, anytime there's a scientific experiment that comes out, a study that comes out, and say, oh, well, I could have told you that. Well, that was obvious. Well, experiments like the Michelson-Morley experiment show that just because things are obvious doesn't mean they're true. They still need to be tested. It was obvious, utterly obvious until around the mid-90s that sugar causes hyperactivity in kids. And then they actually did a handful of studies and then some more studies, and it turned out this was completely untrue. So don't dismiss the fact that a study is done because the results are obvious. Obvious things don't have to be true. How can you make electromagnetic waves? Well, you got an energy source, powers up an RLC circuit with some oscillations. And then if you want that RLC circuit to be transmitting at a different voltage to get a different frequency out of it, you can tie a transformer in there to adapt the voltage. And then you just connect it up through some line to a long pole, an antenna. And the idea is this oscillating frequency that comes out of your RLC circuit, which you can tune to whatever frequency you want, will then produce oscillations in your pole right there, and that will put out your traveling waves to whatever distant point you want to get to, and that's the basis for how radio waves are transmitted. Of course, you know that if you are further and further away from your wave transmission source, you're going to get less and less of the wave. So if you are farther away from a cell phone tower, you're going to get worse and worse reception. If you drive across the country, you'll notice that some stations come in and others go out as you get further and closer to different ones. So the intensity is defined to be the power per area. So power, again, is energy per time per area. But intensity is, in all these contexts, going to be uniform. So you can just say the total power transmitted divided by the total area that it's spreading out over. So to work in terms of intensity, we have this thing called the Poynting vector. And this is a funny spelling of the word Poynting. That's because it was actually named for a guy named Poynting. This was John Henry Poynting. And he actually worked under Maxwell himself at some point in time. It just so happens that his last name is like so fitting for the thing that got named after him, the Poynting vector. It gives the intensity and direction of the power transmission of an electromagnetic wave. So basically, you take the cross product of the E field with the B field, multiply by 1 over mu naught, and you'll get the Poynting vector. So in this little image here, my E field is up, and my B field is, say, to the right. So upright, and you get a propagating wave that travels out of the board. So there you go. So that is your Poynting vector. Now, we know that electromagnetic waves oscillate over time. They get stronger, weaker, stronger, weaker, stronger, weaker, just like cosine functions oscillate. But sometimes it's going to be handy to talk about the average intensity over time. And so for that, you're looking for the time average of the Poynting vector. So the magnitude of the Poynting vector, I'll just multiply the magnitudes of E and B together. They're perpendicular anyway. Divide by mu naught. And then remember, we found this relationship that E over B is equal to C anyway, so I can just plug in for B, E over C. So I'm looking for the time average over a cycle of E squared over C mu naught. These are constants. I'm looking for the time average of E squared over a cycle. And then I can just plug in what E is. It's some E max times sine of something or cosine of something or whatever. And it just so happens that the average of sine squared over its period is a half. So the average intensity of an electromagnetic wave is 1 over 2 C mu naught. What about if you get further away from your source? So electromagnetic waves, when they are caused by a point source, dissipate just like all waves do that propagate out evenly, spherically in all directions. This is called isotropy, when things happen evenly in all directions. So the idea is you've got some source of your wave, it's a point, and it spreads out equally in all directions. And that means that you're taking the amount of power and spreading it out over bigger and bigger spheres. And the surface area of a sphere is 4 pi r squared. So the intensity of your electromagnetic wave at some point is equal to the power of the wave divided by 4 pi times r squared, where r is the distance you are from your source, which means if you go to twice the distance away from your source, you're at 1/4 the intensity. If you go to 10 times the distance from your source, you are at 1/100th of the intensity. So basically, it just dies off very quickly. And the same physics underlies why sound gets weaker when you're further and further away. Sound also follows an r squared dependence, basically, because all waves do whenever they travel out equally anisotropically in 3 dimensions. Another interesting thing to talk about is radiation force and pressure. So if you have light shining itself on a surface, the surface actually feels the pressure from the light absorbing onto it or bouncing off of it. So I'll give you a quick kind of derivation of how the book works through it. So your intensity is your energy per area per time. It just so happens that for photons, the momentum is the energy over c. And so you can just plug that right in here. You get that IA delta t is u. Plug that in for u, and you get this is the momentum of a photon, of a particle of light. Plug it in here, and you get that the force that is caused by a particle of light being absorbed by a surface is the intensity times the area of the surface divided by c. This is if your particle gets absorbed by the surface. On the other hand, your particle might get reflected by the surface, in which case you're going to get a bigger change in momentum. So again, force is change in momentum over time. That's actually how Newton originally wrote it. He didn't write it as ma. He wrote change of momentum over time. So if I am changing direction, then I'm going to have twice the change of momentum. So for perfect reflection, you're going to get the force is equal to twice IA over c. For perfect absorption, you're going to get that the force is IA over c. And then in general, surfaces in general can have some mix of reflection and absorption. Not perfect one way or the other. This is the basis for why a radiometer works. Those little things that spin around when you put them in light. You'll find that if there's actually air in the radiometer, it actually spins the wrong way, because what happens is the black side of the paddles heats up more than the light side, and so what happens is the air kind of pushes it because the air expands. But if you have a radiometer that's actually a vacuum inside, it will follow this. It will feel more of a force on the white side than the dark side, because the white side is reflecting, whereas the black side is absorbing. So as a result, the white side gets a bigger push than the black side does. A quick example, sunlight intensity at the Earth's location is about 1,000 watts per square meter. Visible light's around 1/4 electron volt per photon. Here's the conversion from electron volts to joules. How many photons is this per square meter per second? You can convert the 1/4 electron volts to joules, and then figure out how many of that you need to get 1,000 joules per second per square meter. And you're going to get 2.5 times 10 to the 22 photons. The question is, what's the force per area, which, by the way, is the definition of pressure, if these photons are completely absorbed, meaning you're dealing with this equation right here. So the force per area will just be the intensity divided by c. So you can plug that in here, and you're going to get 3.3 micronewtons per square meter. That'll be your force per area, which again, by definition, is the pressure. And then just to put this in everyday kind of real terms, my average, classroom desk in here is maybe about 2 square meters. So that'd be like 6 or 7 micronewtons. So if you had sunlight hitting a surface of about the size of maybe half of the desks here, half of the desk, you would get, maybe a couple micronewtons. A whole desk could be maybe 6 or 7 micronewtons, which is not a lot, because photons, it takes a huge number of them to do anything substantial, because they just don't have a lot of momentum to them. They have no mass, but they do have momentum, and even their momentum is not that much. So they're pretty easy to stop to the point where it's pretty hard to measure these things. But in space, you can utilize this kind of process for what's called a solar sail, where the difference in the radiation pressures on one side or the other can actually cause the thing to be propelled as you want, for free, basically.